Hello, everyone. My name is Nava. I'm a first-year chemistry student at UCI, and today we will be learning about pseudo-steady state approximation for reactive intermediates. This is also known as PSSA. So, just as an introduction to PSSA, this is a continuation of the topics that we learned about before that include approximating reaction rates and learning about mechanism reactions, so reactions that take more than one step. And we also learned that intermediate and elementary reactions cause complications in calculating the overall reaction rate. Um, this method or idea introduces a new way or an easier way to calculate the overall rate expression. So for expected outcomes, what you will learn in this lecture is to find reaction rates and concentration that include intermediates. Like I said, this is usually more complicated without the use of PSSA. We will also understand the idea of pseudo-steady state and find reaction rates more efficiently. Um, just as a note, this graph was taken from source 4, which will come in the next slide. So more introduction is, this is, like I said, it's a simplified approximation of the overall reaction rate. It mainly applies when K2 is greater than K1. So when the intermediate is consumed faster than it's produced. So these are my sources that I used. So source 1, source 2, source 3, source 4. It will say what source it came from, the picture that I use. For derivation, so just to assume we have a reaction of A goes to B and then goes to C. We've learned that B, which doesn't exist in the products nor the reactants, is called an intermediate. This idea mainly applies when B is created slower than it's consumed. Because of this, we can assume that B in this case is at pseudo steady state, meaning that the change in concentration and the change is 0. So for the following reaction, K1 is the process from A to B, and K2 is the from B to C. As we see here on the right, it's the mechanism is shown. Generally, in order to find the concentration for C, we would be using the following equation, which seems to be very complicated, where we take the concentration of the reactants and then we multiply it by the variables shown right here. Just to note, all the equations and pictures are taken from sources 2 and 3. Like I said, the law that I showed above, or in the previous slide, is complicated, and there's an easier way to derive it using the PSSA. So assuming that B is at pseudo steady state, the expression can be described as the change in the intermediate is always equal to 0. And it's also equal to K1 multiplied by the concentration of the reactants minus the K2 multiplied by the concentration of the intermediate. So these are just the equations to show this idea. Using the mechanism that we showed above, A to B to C, we can derive that the change in concentration for the products is equal to K2 multiplied by the concentration of the intermediate, which is also equal to K1 multiplied by the concentration of the reactants. by simplifying this, we can conclude that the concentration of the products, which is the main goal of this problem, is found by multiplying the initial concentration of the reactants by 1 minus e to the negative k1 times time. Again, these equations were derived from sources 3, and 2. So, for example, we have a reaction of 2NO 2NO plus oxygen gas yields 2 of NO2. So for this is a mechanism reaction. So it has multiple steps in order to reach this final product. For step 1 is shown, and step two is also shown. We can see that N2O2 is canceled, so we can say that the intermediate is N2O2. Using the equation shown in the previous slides, the delta B over delta T is equal to 0. So we can assume that N2O2 is an intermediate that is at pseudo steady state, which means that the change in the concentration for the intermediate is equal to 0. Using the other we can also see here that this is the equation that is derived for the intermediate, which is equal to 0. Using the second equation, we can tell that the concentration of the intermediate is equal to K1 multiplied by the concentration of the reactant divided by K2. Again, using the equation derived in the previous slide, we can conclude that this expression defines the change in concentration of the product. By simplifying this and removing the derivatives, now we can conclude that this expression, the concentration of the product is equal to concentration of the reactant, the initial concentration, multiplied by 1 minus e to the negative k1 times t. So this here is the general rule for pseudo steady state reactions, where the intermediate is assumed to be at a change of 0. So this equation applies for the products. Again, the equations were derived from sources 2 and 3. So to continue on the idea, we can go back and state that without this simplification of the PSSA, the finding the concentration of the products would be very complicated using this equation, which is something that we don't really want to do. Yeah, like I said, this would be the expression to find the concentration of the products. So it's just very complicated, and it takes a long time. Again, all the equations were derived from sources 3 and 2. So in conclusion, the main takeaways from this lesson is that the change in concentration of the intermediate is always equal to 0. As long as the intermediate is assumed to be pseudo steady state, we can assume that the change in the concentration is 0. This is because it's being produced and consumed. So it's being consumed faster than it's being produced. So the change in the concentration is almost 0. We can also take away that the concentration of the product can be found using this equation. So this is very helpful when working with mechanism reactions. This is an important topic because it simplifies mechanism reactions, which are very common. So it just simplifies it and takes away the complicated equation that we saw above. This idea best applies when K2 is greater than K1. So when the intermediate is being produced slower than being consumed. So using the information learned from PSSA, students should now be able to solve for concentration of products using mechanism reactions. So this is the main idea of the um, topic, just for students to be able to solve mechanism reactions and find general rate expressions more easily. Again, the equations were derived from sources 2 and 3. That's it. Thank you.